Hello everyone, and thank you for coming to this presentation on the structure and mechanical properties of prismless enamel in crocodilians. I'm Jack Grimm, and I will be presenting some of the current research that Cameron and I have been conducting under Professor Arola at the University of Washington. We'll start with a brief review of the prismatic microstructure we are used to seeing in mammals and some of the different conditions that crocodilian teeth experience. I will then present the unique microstructure of prismless enamel we've seen before moving into characterization. We use nanoindentation and Raman spectroscopy to look for gradients throughout the enamel thickness, and microcantilever bending to begin to understand the influence of hierarchical structure. The dehydration and cracking behavior is also unique compared to what we are used to seeing in mammalian enamel. Finally, I will suggest some potential applications for this research that we have our eyes on. Why study enamel? As covered in the earlier presentation by Professor Arola, it is a remarkably tough and crack-resistant biocomposite made of roughly 96% hydroxyapatite mineral, 3% water, and 1% organic protein by weight. It is the outermost surface of our teeth and is approximately 1 millimeter thick for humans. Remarkably, it can withstand many cracks without completely failing, thanks to the myriad toughening mechanisms at play, including crack bifurcation, crack deflection, and microcracking. This results in what is known as rising R-curve behavior, meaning that the crack growth resistance actually increases as the crack grows from the outer enamel surface and extends inwards, with the most significant improvement occurring in the inner enamel. The reason for this behavior is the hierarchical microstructure. At the smallest level, it is made of hydroxyapatite nanocrystals that are assembled into prisms or rods, which then stretch continuously from the dentin enamel junction to the outer enamel surface. It is the interface between prisms that is responsible for much of the crack resistance. In the inner two-thirds of the human enamel, the rods weave in decussation bands, further helping to guide cracks. This helps our teeth withstand millions of cycles over a lifetime of use, but crocodilians have some different design constraints and very different enamel structure. The most distinguishing characteristic of crocodilians is they have drastically higher bite forces than humans. This graph from Erickson shows the representative bite force as a function of mean body mass for all 23 extant species of crocodilians. The saltwater crocodile here has the highest recorded bite force of any living terrestrial animal at 16.4 kilonewtons, though the average is closer to 9. American alligators have an average bite force of 5.1 kilonewtons, and for reference, humans are generally in the neighborhood of 1 kilonewton. I've also added the measurements for the tuatara lizard down here, which I will reference later in the presentation. You are probably aware that crocodilians are ambush predators, and when they snap their jaws shut on their prey, it causes a more dynamic load on their teeth, especially when they hit bone. The rapid loading condition and high bite forces put tremendous stress on the teeth. One way that crocodilians have adapted to that is to simply replace their teeth on an annual schedule, but then the enamel, which is only a few hundred microns thick, still has to function for a whole year. Our motivation for characterizing the enamel of these massive reptiles is to understand how it lasts that long. Pictured on the right here is an alligator tooth that has been mounted in epoxy before being sectioned for characterization, and some dental terminology. The face of the tooth that curves inwards towards the tongue, that's the lingual side, and what faces outwards is then the buccal surface. The literature is lacking in thorough material science studies of prismless enamel, and you might not be familiar. So let's take a look at what kind of microstructure is present. On this slide is a buccal lingual section of an American alligator tooth that's been polished and etched, and we're looking at the lingual surface relatively close to the cusp. This tooth was around 15 millimeters tall total, so we're only seeing the cuspal region right here. In prismless enamel, the microstructure consists of repeating arrangements of hydroxyapatite nanocrystals that run primarily normal to the dentin enamel junction in a straight line to the outer enamel surface. Also notice that there are no distinct prism here, just nanocrystals. You can, however, see some growth lines where there is a slight overlap between crystals. However, not all regions of the enamel are so linear. This is another polished and etched buccal lingual section of the cusp of a tooth, this time from a saltwater crocodile. It is possible to see distinct bands where the nanocrystals are parallel to the exposed surface as before, here at the top and the bottom of the micrograph, but there's also this region separating them, where we're looking down at the hydroxyapatite crystals along their long C-axis. Clearly, there is some three-dimensional complexity to the microstructure, so we need to add another perspective. Now we are looking from the cusp down towards the root on a transverse cross-section of an alligator tooth, again polished and etched. Close to the dentin enamel junction, you can see some relatively large gaps separating repeating columns of diverging hydroxyapatite crystals. The boundaries between adjacent columns are then delineated by convergent crystals. I've pointed out some of them in red here for you. The overlap of one sheaf of nanocrystals onto the next causes a slight serration, which is responsible for the so-called growth lines we saw before. The top right micrograph showcases the divergence within a column. The crystals are fanning out from the center axis of the column. Progressing through the enamel thickness, the hydroxyapatite crystals become increasingly aligned, making it more difficult to distinguish individual columns. The final SEM image on this slide shows a fairly sharp gradient near the outer enamel surface. Nanocrystal size and porosity decrease, enabling higher and higher packing density. When we see such an increase in the mineral density, you'd expect a change in the mechanical properties, which is what we investigated next via nanoindentation. Here are the average results of 3 American alligator teeth, all section buccal lingually as shown in the micrograph. The force displacement curve of a representative indent is shown here, with a maximum force of 5 newtons and holding for 5 seconds before measuring the elastic response. We performed indents using an accelerated mapping feature, taking 9 measurements at each of 6 evenly spaced locations along a path through the enamel thickness, with the measurements at each end being within 10 microns either of the surface or DEJ. The location of the measurements is reported as the distance from the DEJ normalized by the thickness of the enamel along the path of measurement. We searched for variations between the buccal, lingual, and cuspal surfaces, but didn't see any significant differences. Data from human cuspal enamel obtained using the same technique is also presented here for comparison. The alligator enamel had lower values for both stiffness and hardness, though the difference in elastic modulus is larger. More interesting is the nature of the gradients themselves. As expected, the outermost layer of alligator enamel was significantly stiffer and harder than the rest, with an elastic modulus of 69 gigapascals and a Berkovich hardness of 3.79 gigapascals. But rather than a gradual and continuous gradient towards the DEJ, as is the case in humans, the properties plateau throughout the middle enamel. The average elastic modulus then drops to 59 gigapascals at the DEJ, but the hardness remains pretty constant at 3.47. This sharp property gradient at the outer enamel agrees with our microscopy observations. The microstructural gradient was most dramatic only in the outer 30-40 microns of the enamel. The next array of indents is evidently beyond the region of dramatic changes in hydroxyapatite nanocrystal size and packing. Regardless, a harder surface layer improves the durability and wear resistance of the enamel, while a softer interior would transitions to the dentin. To reinforce our spatial understanding of the enamel, we conducted Raman spectroscopy in the same positions as the nanoindentation. The 2 features we will be considering for this analysis are the 961 phosphate peak and the 1069 carbonate curve. Following our experience and the guidance of literature, comparing the ratio of the area under these 2 peaks reflects the amount of carbonate substitution that has occurred in hydroxyapatite. Similar to humans, we see a gradient in alligators with the inner enamel being significantly more carbonated than the outer layer. And similar to the observations from our nanoindentation, the gradient is quite sudden. Compared to humans, alligator enamel has significantly higher level of carbonated hydroxyapatite, though the difference is not quite so large in the outermost region. We also noticed that the measures of carbonated content were persistently higher for the cuspal surface, and we're still looking into that, since we didn't see any change in the nanoindentation. The other measurement we got from Raman was the full width at half max of the phosphate peak, which reflects the degree of crystallinity. A more pure and fully crystallized sample would have a narrow peak, thus a broad peak should reflect a lower crystallinity, for example, caused by higher organic protein content or gaps between the columnar units. Again, the measurements line up well with the microscopy and the nanoindentation gradients. We see that the highest degree of crystallinity in alligator enamel is at the surface of the tooth, while it decreases pretty sharply and significantly moving towards the dentin enamel junction, which is exactly what we expected looking at the microstructure. The frequency and size of intercolumnar gaps decreases the closer you get to the outer surface. Interestingly, the narrowest phosphate peak width measured in alligator enamel is still wider than the broadest measure from humans. One possible explanation for this is a higher protein content, but a thorough quantification of the composition needs to be conducted before we can make any solid conclusions. One issue with characterizing hierarchical biological materials is it is difficult to deconvolute the contributions of each level of hierarchy to the total properties of the bulk material. Microcantilevers offer a potential solution for this dilemma, as the dimensions can be tailored to capture specific features at a desired size or orientation. These small cantilevers are fabricated directly into the polished enamel surface using a focused ion beam to mill out trenches of enamel at an angle, resulting in the triangular geometry you see here. Then we brought them to the nanoindenter, which lets us measure the displacement and load applied near the tip of the cantilever. You can see the beams deform elastically before sudden failure, where the displacement would jump by a few microns. We then converted the force displacement data into stress and strain, accounting for the triangular cross-section of the cantilever, and the results are presented here in this table. We got an average modulus of 41 gigapascals and a bending strength of about 580 megapascals. These values line up quite well with the reported values from a microcantilever test in the prismless enamel of the Tuatara lizard, though ours had greater variance due to poor dimensional control. Compared to the intraprismatic enamel of mammals, that is, the hydroxyapatite nanocrystals within a single rod, prismless enamel is weaker and more flexible. This is probably due to the higher protein content suggested by Raman. All three of these microcantilevers were located in that middle enamel region, so the properties should be pretty close to each other. The fracture surfaces of these microcantilevers show some interesting behavior. On AM1, the crack propagated along the long side of the nanocrystals, as indicated by the relatively smooth surface. Below that, we see a rough surface that looks somewhat like fiber pullout in composites. And indeed, enamel is a biocomposite. It is not clear in AM3 if the crack solely went around the nanocrystals or if it transversely fractured through some of them. This last example here shows sort of a stair-step serrated pattern, a combination of the other two, likely following the growth lines separating the hydroxyapatite crystals. This top-down image shows that the fracture surface is not completely perpendicular to the cantilever, but actually has a little bit of slant to it. In each case, the microstructure is clearly influencing the cracking behavior. These beams on the bottom here had fracture surfaces that made the calculations impossible for stress and strain, but the highly oblique surfaces add more evidence to tell us that the alligator enamel is capable of guiding cracks. This is a critical characteristic for improving the damage tolerance of enamel. The final preliminary investigation I would like to share with you all is the susceptibility of alligator enamel to dehydration cracking. This GIF shows the buccal surface of the tooth looking towards the interior dentin, with a delta Z of about 30 microns between each imaged layer. This region in the middle is the dentin, but more interesting is the extensive network of cracks that form throughout the enamel, both in the long direction of the tooth from root to cusp and circumferentially. The result is these cells of enamel separated by cracks. And these cracks are quite deep. If you watch closely, you can notice that the positions of the cracks do not really change as you move through the enamel. You can also see the extent of the cracks in this buccolingual section micrograph here on the bottom, where in just about a millimeter, we see 3 large cracks stretching through the entirety of the enamel. Numerous smaller ones, you can also see those closer to the DEJ. The increased frequency of cracks combined with the direction of the crack, you'll see that on the next slide, tells us that the cause of these cracks is the shrinkage of the dentin tissue, which experiences much larger dimensional changes with hydration than enamel does. Looking a little closer, we can see the direction that the crack bifurcated here confirms that the crack had to originate at the DEJ and move towards the OES. You can also see towards the bottom of this center micrograph the gaps between columns which are serving as seed cracks that are then propagated during dehydration. The crack stays mostly straight with some slight deviations to accommodate for the kind of sinuous serrated interface between columnar units. The bifurcation itself seems to be initiated on a growth line, where a new layer of hydroxyapatite nanocrystals fan out from behind the previous layer. The crack paths then follow the same divergent trajectory as the crystals spread away from each other. Rotating our perspective to look at the lingual surface head-on, we're now looking at one of those long root-to-cusp cracks. This crack can be seen to bifurcate at a point of triple convergence. On each side of the crack, you can see the nanocrystals kind of leaning in towards each other, meaning that this must be an intersection of 3 adjacent columns. Remember that each column was defined by crystals diverging from the center of the column, so then the boundary between them is convergent. This boundary is evidently capable of guiding cracks as well, bringing more control of the possible paths a crack can take and improving the damage tolerance. To summarize, we have observed that crocodilian enamel, even though it lacks the prismatic structure common in mammals, has other features that help it maintain a functional tooth under incredibly high bite forces. While the teeth may only be temporary by design because of their regenerative ability, while in use, it is subjected to forces up to 16 times that of a human jaw, a more dynamic loading rate, and a greater risk of impact into other hard tissues such as the bones of prey. The microstructure of the enamel displays some patterns and complexity that presumably have evolved to survive the extreme conditions, but they have not been comprehensively described in the literature yet. Using nanoindentation in Raman spectroscopy, we found gradients in the properties and composition, with the most dramatic changes occurring in the outermost layer of the enamel to improve the wear resistance. but overall the properties were lower than human. The prismless microstructure is found to be capable of guiding cracks, as evidenced by both the fracture surfaces of microcantilevers and the cracks caused by dehydration. Some potential areas that we think these findings will be useful for include amylogenesis imperfecta research and the design of impact-resistant ceramic armor through the use of rotational 3D printing. Amylogenesis imperfecta is a genetic disease that interrupts the formation of enamel, and as seen here in a mouse model, can result in a prismless microstructure akin to that in reptiles. Teeth afflicted by this disease are weak and easily damaged, so characterization of a successful prismless enamel structure, like in crocodilians, is necessary before the critical flaws of this disease can be understood and treated. In contrast, crocodilian enamel has some similar design criterion to armor or other impact coatings. Namely, it's a thin layer that experiences high loads applied in a very rapid fashion. Perhaps the teeth could serve as a model for bioinspiration. One way to synthetically produce the types of microstructures seen in an alligator enamel would be through rotational 3D printing, which has been shown to be capable of aligning reinforcement particles in a composite. This figure is from a paper emulating the osteon structure of bones using carbon fibers, but alumina platelet alignment in a ceramic slurry is also feasible. I would like to give special thanks to my advisor, Professor Arola, as well as my fellow researcher, Cameron Renteria, for all their help with this project. Our research wouldn't have been possible without the generous donations of alligator and crocodile teeth from Ruth at the Rockefeller Wildlife Refuge and Tom at Reptile Gardens. This research was funded through the Distinguished Graduate Research Program operated by the Pacific Northwest National Lab and the College of Engineering at UW. Thank you for your attention, and I hope you have a great day.